This video is going to be an introduction to pendulum motion, but before we do that, we're going to take a quick review of a mass on a spring as the simple case of simple harmonic motion, just as a review of what we did the first time through, because we're going to follow a very similar path when we talk about the pendulum. So we're going to start on the left side with the mass oscillating on a spring, and we have a couple expressions for the motion here. For the position, we have that the position as a function of time is equal to the amplitude times cosine of omega t, where cosine omega t represents the cosine of the angular frequency times the time. If we had a phase shift, we would have to add in a plus phi, but we're going to leave that out for right now just to simplify it. Taking the derivative, we can get the velocity as a function of time, which is omega, negative omega, times the amplitude times the sine of omega t. Take the derivative again, and we get the acceleration as negative omega squared times the amplitude times the cosine of omega t. If we rearrange the acceleration function, we can also get that our acceleration as a function of time is equal to negative omega squared times the position as a function of time. We're going to be doing something very similar for the pendulum, but before we do that, remember that we also came up with an expression for the period of a simple harmonic oscillator. And for a mass on a spring, we found that to be that the period is equal to 2 pi times the square root of mass over the spring constant. Now, obviously, this last equation is going to change for a pendulum because we can't have a spring constant. We don't have a spring anymore. But we're going to start just by going through the derivation of this period equation again, because again, we need to follow the same exact process when we get to the pendulum. The way we came up with this was by going back to Newton's second law, and we said first that we had an acceleration of k over m times x. And to see where this comes from, just multiply the mass back to the other side. You would say that mass times acceleration is equal to Hooke's law, kx. And we just divided both sides by the mass. There should be a negative on both of those. Negative km times x. Now up here in pink we also have this other expression for the acceleration. And since we have two expressions for acceleration, we set them equal to each other. And we said that negative k over m times x is equal to negative omega squared times x. We canceled out our x's, we canceled out our negatives, and we said that omega is equal to the square root of k over m. Now we also have that our period is equal to 2 pi over omega, where omega is the angular frequency, and we just found out what omega is for a mass oscillating on a spring. So we took the square root of k over m, we plugged it in for omega, and that's how we got this expression. Okay? Again, same process for the pendulum. For the pendulum, we have two kinds of pendulums. The first one is a simple pendulum, and this is a point mass at the end of a spring. At the end of a string, I'm sorry, no springs here, at the end of a string. And the other case is a physical pendulum, and a physical pendulum is anything where we actually care about the shape. So we're going to start with the simple pendulum first, because that's the easiest one to work out. For a point mass, we know our moment of inertia is just going to be mass times the radius squared. For the physical pendulum, we have to leave moment of inertia in the equation because it's going to change each time. For either one of these, though, we can come up with similar expressions for the position, velocity, and acceleration, the same way we did for the mass oscillating on a spring. For either of these pendulums, the path that they're going to follow is going to be a circular path. Okay? It's going to sweep out part of a circle. Because it's a circular path, now we need to treat this as rotational motion. So instead of regular old position, we're going to want angular position or angular displacement. That's a theta. Okay, so our First equation for the pendulum is going to be that theta as a function of time, instead of x as a function of time, theta as a function of time is equal to our angular displacement, theta max, times the cosine of omega t. Take the derivative, and we get that the angular velocity as a function of time is equal to the angular frequency times theta max times the sine of omega t, and taking the derivative of cosine, we get a negative sign that goes out in front. Now be careful here. This is angular velocity. This is angular frequency over here. Yeah, they don't cancel. They're not the same thing. They use the same symbol, but they're not the same thing. Let's take the derivative one more time to get an acceleration function. Angular acceleration, alpha as a function of time, is equal to negative omega squared times theta max times the cosine of omega t. Again, all three of these could have a phase shift. We're leaving it out to simplify at the beginning. And just like we did before, we're going to substitute our angular displacement function into the acceleration function, and we have alpha as a function of time is equal to negative omega squared times theta as a function of time. Okay, so very similar so far. Let's take a closer look at why the pendulum works and why we can consider this simple harmonic motion. Our reason for the spring being simple harmonic motion is that it has a constant restoring force, namely Hooke's law, F equals kx. For the pendulum, if we draw it out, we see that the pendulum has a restoring force provided by the force of gravity. There's this angle theta at the top of the pendulum, the angular displacement of the pendulum. There is the weight of this thing pulling the pendulum downward, so this is mg. And we can break this into components. The two components are going to be a horizontal and a vertical, and that's rotated. So we have perpendicular and parallel to the pendulum spring, or the pendulum string. The one that's perpendicular is going to be mg sine theta, and the one that's parallel is going to be mg cosine theta. The mg sine theta is responsible for the pendulum entering rotational motion. That's providing a torque. Okay, so this thing is rotating. We're at the pivot point up at the top, and the force responsible for that is mg sine theta. So the torque responsible for that rotation is this force, mg sine theta, times the length of the pendulum spring. So we could say that the net torque on this is going to be mg sine theta times the length of the pendulum. We're going to make a simplification here because this sine theta term in the torque equation is going to give us a little bit of a headache. We're going to make something called the small angle approximation, which your textbook talks about in a little bit more detail. And what that says is that for small angles, sine theta can be approximated as theta. And if you don't believe this, try it on a calculator for really small angles. So plug in 5 degrees, and the sine of the angle is going to be almost exactly equal to the angle measure in radians. And so this is true. You can test it out if you don't believe it, but this is true, which means that we can replace the sine theta with just the regular old theta. So net torque is going to equal mg theta times the length. Just like in linear, where we have an acceleration that is proportional to the position, so a equals k over m times x for linear. We're going to get a force and therefore an acceleration that's proportional to the angular displacement. So same thing. Simple harmonic motion requires acceleration proportional to the displacement, whether it's linear or angular displacement. So we need to get some kind of expression for the acceleration out of this. Remember that torque is also I times alpha. So we can replace that and say I times alpha is mg theta times the length of the pendulum. So that makes alpha mg theta times the length over the moment of inertia. So far, all of this has been for both a simple pendulum and a physical pendulum. Now is when we need to differentiate between the two, and again, we're going to do the simple pendulum first. So let's go to a new slide here. So for the simple pendulum, which again is just a point mass at the end